So it will satisfy the equation. The reason we like sines and cosines is because after you find the solution in terms of sines and cosines, you can express any other wave in terms of sines and cosines. So, and if you're anxious, how much you need to know, I'll tell you. Okay? I will, toward the end, I will mention what we need. So here's the solution we're seeking. We're looking for after this solution. Some electric field equals to some amplitude of the electric field times the cosine of kx minus omega t. And then some magnetic field equals to E naught times the cosine of kx minus omega. I just need to modify one thing. I wanted it to travel in the z direction so that the electric and magnetic fields would have some x and y components. It's just easier to draw them before. So this is z. Right, so K is called the wave number. We have seen it before, right? We've seen it in mechanics. The wave number, okay? Is the wave number. And it's equal to 2 pi divided by the wavelength. Lambda is the wavelength. Omega is the angular speed. Or angular velocity. Or the angular frequency sometimes. It's 2 pi over the period. 2 pi over the period. If you divide omega by k, what do you get? You get omega over k equals, well, let's see, 2 pi over the period over 2 pi over lambda. And that's equal to lambda over the period. And the wavelength over the period is the wave speed. Is the speed of the wave. And at what speed is our wave traveling? Let's see. Yeah, speed of light. So in other words, omega is equal to c times k. That's the relationship between omega and k. The speed of light, of course, is basically 3 times 10 to the 8, right? Meters per second. Okay. Now, if you go back to the divergence of E and divergence of B being 0, you will see that E and B cannot have a z component. They depend on z, but they do not have a z component. For the sake of time, I'm probably not going to go over that. So basically, here's what we have. Here's the x-axis. Here's the x. It's always hard to draw in 3D, right? Here's the x-axis. Let's see. Now let's draw just vertical enough. So here's the x-axis. Let's make the y-axis this way, okay? And here is z. I definitely need to learn how to draw 3D. Just still, that's good. Let's say my electric field only has an x component, just for the sake of simplicity. Here's my electric field. It has some x component. My magnetic field will have a y component. Also, it's because of the curve between them. If one of them has x, the other one will have y, and the propagation is in the z direction. Also, for the sake of time, I don't want to spend too much time on that. So this is E, and the magnetic field, I'm trying to say it's in this direction. It's in the y direction. Okay, so the magnetic field is in the y direction, the electric field is in the x direction, and they propagate in this z direction. Okay. This is E. yeah, it's okay. You can pick sign.
Yeah,
like-
because the magnetic field is
Yes,
a shift. Okay.
exactly. Yeah, there will just be a phase shift if you choose sign. I think the book also chooses cosine, although it could be.
But they're
It
both,
doesn't matter.
Yeah, they're both always the same though, because they're perpendicular, right?
Yes, they are
Phase shift of
perpendicular,
90.
and because of their derivatives, yes, it would be the same.
So if you pick side for one, other one.
Yes, yeah, yeah. So that's that, and then if I relate the curl of E and B, I would arrive at the following equation, which for the sake of time, I'm going to just skip through it. The magnitude of B and the magnitude of E, how are they related? So this one also, E0 would equal to B0 times the speed of light. There, that's just because of the problem. So, if you're interested, drop by during office hours, maybe after the final or something. I'll be happy to go over it with you. I just don't want to do that. I want to get into the homework problem. Okay? So that is that. Now, if you curl your hand from E to B, the curl of E cross B will give you the direction of the propagation. So twist your fingers from E to B, and you will get your thumb this way. So basically, E cross B will give you the direction, would be a vector that points in the direction of propagation. E cross B is a vector that points in the direction of propagation. Now, how much energy do electromagnetic waves carry? Let me put that here. You may recall that the total energy, you've got an electric field and a magnetic field both traveling. So the total energy density would be the energy density in the electric field plus the energy density in the magnetic field, right? And the magnetic field. The energy density in the electric field would be 1/2 of epsilon naught times the electric field squared, right? Where the electric field is this, E naught times the cosine, the whole thing squared. We'll worry about that in a moment, about the cosine. But for now, let's just write it E squared. And for the magnetic field, it is 1/2 mu naught times the magnetic field squared, right? Now the magnetic field squared is equal to the electric field squared divided by C, because their amplitudes are related this way. So B naught is just E naught over C. So this one, magnetic field squared, would be the electric field squared over C squared, right? Does that make sense? So you got B naught squared would be E naught squared over C squared. So you would have 1/2 epsilon naught E squared plus 1/2 mu naught B squared, but B squared is B squared over C squared. But mu naught times C squared is actually just epsilon naught. It's just epsilon naught. Does that make sense? Because what is 1/C squared? It's epsilon naught mu naught on the numerator. You can cancel the mu naught, right? Because what did we say? Yeah, here. Epsilon naught mu naught is equal to 1/C squared. So 1/C squared can be replaced by epsilon naught mu naught in the numerator. You cross about, and you got your energy density equal to 1/2 of epsilon naught E squared plus another 1/2 epsilon naught E squared. So the magnetic field carries the same energy density as the electric field. And so the energy density is epsilon naught E squared. Epsilon naught E squared. That's the energy what? Density. Energy per unit of volume, right? Energy per unit of volume. Now I would like to calculate the energy, and then the power, and then the intensity. And then it would be the energy. Now the energy would be the energy density times volume, right? So you get your electromagnetic wave traveling, let's say, in this direction. So here is your electromagnetic wave. It's traveling in this direction. Obviously, you got a bunch, many of them, a whole volume of them traveling this way. And let's say they cross they pass through an area A. This is an area A. And if you wait for them over a time delta t, how far do they travel in a time delta t? Let me call this here. This is delta x. Or since they're traveling in the z direction, it would be delta z. And how far do they travel in a time delta t?
Delta z.
In a time, it would be delta z, but it's the speed times time, right? Speed times time will give you distance. But what's the speed?
Speed of light.
C times delta t. C times delta. That's the speed. Speed times time gives you the distance. So the amount of volume that they have filled is A times the thickness, right? So A times delta Z. So it would be A C delta T. So delta U, which is the energy, would be little u times the volume. The volume. Which is delta U, I'm sorry, U is epsilon naught E squared. And then the volume is we said the area times C times delta T. Let me divide both sides by delta T. Delta T, delta U over delta T would be epsilon naught C times A or times E squared times A. What is the energy per unit of time?
Power.
Huh? Power, yes. Capital P for power. Power is the energy over time. So the intensity, I, for intensity, would be the power over area, and you would get epsilon naught times C times E squared. That's the intensity. Now, this is the instantaneous intensity, right? Because remember, E is a function of the cosine. It's a function of t, cosine something. So we usually don't want the instantaneous, we want the average intensity. So let me write down what is inside the E. So remember, for the E, you have this, epsilon naught times C. So E squared will be E naught squared cosine squared. So it would be the amplitude squared, E naught squared times the cosine squared of omega t kz minus omega t. And now the question is, what's the average of a cosine squared? It's 1/2, yes. Because think about it. What's sine squared plus cosine squared? 1. So on average, sine squared plus cosine squared, they're always 1 when you add them in. So, well, cosine would take half, and the sine would take the other half. So the average of the cosine squared is 1/2. So the average intensity, so we'll write here I average is equal to, and sometimes, by the way, people just write I. And it's, so it would be 1/2 epsilon naught C E naught squared. So that's the average intensity. Okay. I think we know enough to do the rest of the problem. I know I skipped some steps. I didn't convince you that there's a cross product, which is the direction of the propagation. But those are details. So I want to do the rest of the product here. So, by the way, I need to erase the boards here. Give on, yeah.
Will we ever use instantaneous intensity?
I'm sorry?
Will we ever use instantaneous intensity, or we only really care about
It's
average?
possible, but nobody, yeah, usually you want this. So, I will leave this board, so if you need it, please. So I'm going to go to the next problem that we have, which is, it says a helium neon laser, so, which is 31.19, right? 31.19. So you got a laser emits 1 millimeter diameter beam with power of 1 milliwatt. The power is 1 milliwatt. So the beam, basically, you got a laser beam that's coming this way, and it will hit a certain area. And that area would be, you got the diameter, so you can calculate the area. So you got a laser beam basically shining on a certain area, right? That's the laser beam shining on a certain area with a certain power. So you have the intensity. Because you have the power and you have the area. Power over area is the intensity. And so the question is, find E0 and E0. So the solution is, first of all, the intensity is the power over the area. The power is 1 milliwatt, so 1 times 10 to the minus 3. The area is pi r squared. What is R? Half a millimeter, right? So 0.5 times 10 to the minus 3, right? Because it's millimeters. And you square it, and you get an intensity of 1,270 watts per square meter. That's the intensity. Well, once you know the intensity, you can use this to get the electric. So use this now. So you got the intensity is 1/2 epsilon naught C times E squared, E naught squared. So E naught would be 2I over epsilon naught C squared. So you can plug in the numbers. You got E naught would be 2 times I, which is 1270. Epsilon naught is 8.85 times 10 to the minus 12, right? And C is, of course, 3 times 10 to the 8 meters per second. And this gives you the electric field. Electric field turns out to be about 980 volts per meter or newtons per coulomb. Once you know E, you can figure out what V naught is. What is V naught? How is it related to E?
E naught divided by C.
E naught. E naught divided by C. E naught divided by C. So you get 980 over C, which is 3 times 10 to the 8. I guess 3.26 times 10 to the minus 6. That's what I got. So I'm going to erase it, right? next question is 13, not 13, chapter 31, 31.49. 39.49. It is, you got the electric field, they say the maximum electric field strength. So basically they're giving you E naught. So given this, E naught is 3 megavolts per meter. So 3 times 10 to the 6 volts per meter. And so they say find the power. So suppose this electric field is impacting an area of a certain diameter. Find the power if the diameter, I'm paraphrasing diameter, if the diameter is 1 centimeter. So use your intensity formula. Let me start here. Intensity is this. So if the intensity is 1/2 epsilon naught times C times E naught squared. But remember, intensity is power, right? Over area. It's the power over the area. So if I multiply both sides by the area, I will get the power, which is what I want. So the power will be 1/2 epsilon naught C area E naught squared. So substitute. You have 1/2 8.85 times 10 to the minus 12. 3 times 10 to the 8. The area is pi r squared. The diameter is 1 centimeter. Is it 1 centimeter? Yes, it is 1 centimeter. So 0.5 centimeters for the radius times 10 to the minus 2 to change it to meters. And then squared. You have pi r squared for the area. And then E naught squared. The electric field is 3 times 10 to the 6th squared. So that gives us a power of 9.4 times 10 to the 5 watts. That's the power.
Also,
Yes.
Isn't so since we use the average intensity, isn't this the average power?
Yes. Yeah.
so if the question is asking for maximum power, right? So why don't we use the without the 1/2, basically?
Let me see.
Because if you this power formula doesn't have the 1/2, right? That's instantaneous power.
Yeah, let me check. What are they saying here?
They're asking for maximum force.
Yeah, if it's the maximum power, then yeah, you would use the one with the cosine equal to 1. Yeah, you're right.
Yeah,
Without
so
the 2.
it's basically that same thing times 2.
Times 2, yeah. Yeah. So, yeah. But I think what probably the author really meant is to find use the average power.
Okay.
Yeah. So, yeah. Let's see. Just one more. It says for this one is a LASIK vision correction system. So you heard of LASIK, right? Okay. So correction system, it uses a laser, and that laser uses it emits pulses of 10 nanoseconds. They're like 10 nanoseconds long. So 10 to the minus 8, right? Because 10 times 10 to the minus 9 is a nanosecond. And then they give energy in each burst. They give you 2 millijoules, right? 2 millijoules. And they say the laser beam is focused on a 0.85 diameter circle on the cornea of the eye, right? And the question is, what is the electric field amplitude? What's the electric field amplitude? What's the electric field amplitude? So, and this problem is 950. 31.50. So you have this, 2.5 millijoules of energy are given off in time delta t equal to 10 nanoseconds. The energy is impacted or impacted on a circle of diameter 0.85 millimeters. Find T0. They want the amplitude. Find the amplitude. Solution. You have energy and you have time. What do you do with that? Power, right? Yeah, you have the energy. It gives up 2.5 millijoules in this much time. So the power is 2.5 millijoules, so that's times 10 to the minus 3 divided by the time, which is 10 times 10 to the minus 9, right? Because nanoseconds means times 10 to the minus 9. So you get 10 to the minus 8 becomes 10 to the 8, so this becomes 2.5 times 10 to the 5th. Therefore, the intensity, which is the power over the area, would be 2.5 times 10 to the 5th over the area. The area is pi r squared, so pi times r squared. R is 0.425, you said? Millimeters, right? So times 10 to the minus 3, and we have to square. And I don't think I have this number. If you can help me, that'd be great. 6 to the 11, I guess. Give me something times 10 to the 11. Watts per square meter because it's an intensity. Now they want the magnitude of the electric field. We're going to use this one, right? Yeah. So we find the electric field. So using that formula, so you get E naught would be 2 times the intensity divided by epsilon naught times C squared. So you get 2. Times the 4.406, I'll put it 4.41 times 10 to the 11 divided by epsilon naught, 8.85 times 10 to the minus 12 times C, which is 3 times 10 to the 8 square root of the whole thing, and we got your E naught to be 1.8 times 10 to the 7. Volts per meter. Hopefully that's sounds good. Thanks.
So,
Yeah.
when do we usually use the cosine squared formula? Do we not use it?
In all these problems you don't. If we're interested on average, what happens, right?
So,
Yeah. Because your pulse, usually when you send a pulse, you don't send it for like 0 seconds, right? You have to send it over a period of time, so you get the average.
So the power we saw for over there is really the average power?
Yeah, it is the average price. So, I mentioned earlier, for people who had me yesterday, you already have worksheet 15. Let's do this. Let me pause the recording. Just want to tell you what we need.